Okay, this is Dakari Abbott presenting group number one's stuff. I covered chapters 2.3 and 2.4. 2.3 covers best practices to use in writing proofs. So all proofs operate on assumptions, essentially, or you wouldn't be able to get anywhere. And assumptions are any prior things that have already been proved, in a proof or otherwise. And you can use any assumptions as long as you list them at the beginning of your proof, and they're obviously valid. But in the material of the book, they've given us a few assumptions that are, built in. Like the rules of algebra, which is pretty common in all proofs. The set of integers is closed under addition, multiplication, and subtraction also, Every integer is either even or odd. If x is an integer, there is no integer between x and x plus 1, given. The relative order of any two real numbers, also a given. The square of any real number is greater than or equal to 0, also a mathematical whatnot. Okay. Next up, they follow a typical structure. You need assumptions to make them work. Otherwise, you'll have to just go through all of the knowledge of human history to set up your wherever you're at. You know what I mean? We wouldn't improve without assumptions. But you have to be clear about them. Just like you have to be clear about your speaking. The whole point of a proof is to give your ideas to someone. So if you're not communicating your ideas clearly, then you're going to run into some issues. You're not accomplishing the goal of the proof. You're not proving anything to them because they think you're stupid. So language is necessary in communication. And proofs are communication, so language is necessary in proofs. There's a standardized language accepted with proofs to help communicate. And there's a couple of basic transitional phrases is really what it is in between the math, in between your actual work that's being done. So there's words like thus, these are all just kind of basic transition words. I don't know that there's too much value in going over what they're used for. If you know English, then you know where you would use those in a proof, and they help to add context to all the math equations. You know what I mean? Your reader may not be as high of a level as you. They may not follow the line of thought that you're intending to lay out. So utilizing transition words like this in between, gives and yields at the start of maybe X, gives and yields at the start, at the end of an equation, right? So if you transferred an equation into something else, but gives and yields, even if it's an allowed assumption that the math that you did inside to give and yield something new, then you still want to put that, you don't want to just go from one equation to another equation and them not understand how you got there. So using transition words like this helps, by definition, by assumption, you can help to, remind your user or your reader of stuff that they need to know to understand where you're going in the proof. So as said, proofs are communication. Effective communication requires clarity, and for that, there's been established a list of best practices. So the general rules, maybe not rules, but how people like to set up their proofs, right? So a clearly laid out beginning and ending, obviously, for any type of communication, you want something like that. In the book, they had a little square black dot to denote the ending. At the beginning, they just put proof and a colon. It could be, you could say beginning and ending, or you could say, here we go, and that was that. Whatever clearly denotes that there's a start and an end to your proof. Like say, write in full sentences, including your math equations. So those transitional words can help you to convert your non-English, non-sentence flowy math equations into sentences, so it sounds like your proof is just someone explaining something in a class. You guide the reader, as said, you want to clearly communicate your ideas, and you kind of walk them down the pathway. So if there's a lot of complex stuff that you've covered, you might take a break in the middle of the text to go and review, some of the assumptions. Here's where we've got so far. Here's what we still have yet to accomplish to get to the goal of the proof. Maybe some extra clarity on the assumptions. Introduce all your variables. How are they going to know what you're talking about if you don't tell them what you're talking about? Variables are placeholder names. They're not actual numbers or, values you may be using in a proof. Introduce sets of equations with English text and justify all non-algebraically derived steps. Like I said before, assumptions, like algebra is an accepted assumption. But if you're doing some calculus or some trig substitution or something like that, then you're going to have to put that in there in case if your reader doesn't understand, where you got it from. All right, and then existential instantiation is basically the law behind of naming variables, right? So you tell us all the variables that you have at the start. Existential instantiation is the concept that anything that exists can be given a name as long as that name is not presently taken by something else. So you can't have two variables that relate to the same number value. There would be no use in that, first of all, and it would be confusing, second of all. Well, I guess you could have two variables that relate to the same value, but you can't have two variables of the same name, basically. So you can't take the name, and you're good to go, right? So we could have x and j here could be equal to each other, and that would be okay. But to reuse x again, or reuse j again, would be false. I'd have to, like for this down here, this would be equivalent to x, and it would be okay to make like this j was instead to be O, that would be valid by existential instantiation. But it would be invalid to have j equal to -1 and j equal to 11. Try writing a program and pulling that off. And then there's obviously some common errors people will run into. Following rules like this, they can tend to generalize from examples, which will, making universal statements instead of actually proving a statement's universality first. And to do that, you have to either prove whatever statement for every element in your chosen domain, or just pick a generic element for the domain and basically convince the audience that that is a universal statement. You can't just make a logical, a flawed leap of logic, right? Skipping steps, for clarity of the reader, and it could also cause flaws in your math later down the line. Further, there would be circular reasoning, using the fact you're attempting to prove in the proof itself, you know what I mean? So, like, define a ballpark. Oh, well, it's a park where you go and play ball, you know what I mean? You're not giving the person who doesn't understand the idea context that they have, you're not using information they may already have or building information for them so that way they understand the new concept. You're just kind of throwing the concept at them, and it's, a logical fallacy. And assuming facts, once again, you have to write out your assumptions at the start in the proof. You have to reference them, or you have to prove them along the way and then give a little review. Like, here's, the thing that we proved. We're going to act as this is an assumption in the next section of the proof, whatever. On to direct proofs in 2.4. Okay? Direct proofs all follow a certain syntax. The basic idea is a direct proof of a conditional statement assumes the statement's hypothesis to be true and proves the statement's conclusion as a direct result of this assumption. So, the hypothesis is assumed true. You don't have to go through whatever effort. They follow a general structure, name a few objects, state a few assumptions about those objects or any laws you plan to use in the proof, and then state where you're trying to get to in the proof, and bippity boop, it runs through here. Now, obviously, this was a longer form proof at some point, but they have their declaration, and then they work in They clear out their assumptions. They have their transition words, like by definition, this follows that, where they're clearing up some of the unclear mathematical jargon. And proofs are often much longer in exception. Like I said, they kind of work around long paths like a math equation will tend to do. And in the end, you can summarize it up to be something nice and clear, like we have back here. But yeah, that's that. That's my half of the presentation. Sorry, I went 40 seconds up.